Hi everyone, my name is Dr. Val. Welcome to the YouTube channel for A-level chemistry. This video is all about Le Chatelier's principle, which is when a reaction is in equilibrium, what can we do to that equilibrium to change the position of equilibrium? So we'll look at things like changing the temperature, changing the pressure, adding a catalyst, and we'll see how that can influence the position of the equilibrium as well as the rate of the reaction as well. So we're going to look at that with several worked examples. If this video is helpful, remember to like, subscribe, and please keep checking back. Okay, so we're talking about reactions that are reversible. That means that there's a forward and a backward reaction going on. So it's not a one-way process where reactants go to products. You've got reactants going to products and products going to reactants. So this is normally shown in a chemical equation by a double-sided arrow. So you've got an arrow going from left to right, that's showing the forward reaction, and an arrow going from right to left, that's the backward reaction. Now when a reaction is at equilibrium, both of these processes are still happening. The temptation is to say that the reaction is finished, but actually what's happening is that the rate of the forward reaction equals the rate of the reverse reaction, so it appears that the reaction has stopped, but actually if you could zoom in, see what's happening, the two processes are just cancelling each other out. So the rate of the forward reaction equals the rate of the reverse reaction. And at that point, the position of equilibrium is at one given place. However, we can change that position by changing things like temperature, concentration, and so on. And Le Chatelier's principle tells us what happens if we make changes to a reaction that is in equilibrium. So once a reaction has reached equilibrium, we can change the position of equilibrium. And Le Chatelier's principle goes as follows. If the conditions of a reversible reaction are changed and they disturb the equilibrium, the composition of the mixture will tend to change so as to restore the equilibrium and minimize the effect of altering the conditions. So in other words, whatever you do to a chemical reaction that's in equilibrium, it will try and undo the change that you've made to minimize the change. So the reaction will try and counterbalance any changes it's subjected to. And it's best illustrated by looking at the two examples that we're going to go through, and I'll try and explain each one. So here you've got hydrogen and iodine reacting to form HI. It's a gas phase reaction, and you're told that delta H is 26.5 kilojoules per mole, and that's a plus sign there. That means the reaction is endothermic. Okay. And secondly, there are 2 moles of gas on the left-hand side and 2 moles of gas on the right-hand side. And the question says, use the information given below to identify the most favourable conditions, temperature and pressure for the reaction in order to get a high yield of hydrogen iodide. Your answer should include an expression for the equilibrium constant Kp and an explanation for the conditions that you suggest. How will your conditions impact upon the rate of the reaction? So firstly, let's start by writing the Kp expression. Kp, capital K, because it's an equilibrium constant. So that means the equilibrium constant in terms of pressure. And that's equal to the pressure of the products. So that's the HI. But because there's 2 moles of the HI, it needs to be squared, divided by the pressure of the hydrogen times the pressure of the iodine. So that's your Kp expression. And the question basically is asking, how can we make more HI by changing the conditions? Well, the forward reaction is endothermic, and what that means is an endothermic reaction likes to take in heat energy. So if we want to shift the position of equilibrium so as to make more HI, we're going to end up using a high temperature. Okay, a high temperature will favour the endothermic process. So we'd use a high temperature. This question doesn't require you to do anything in terms of numbers or calculations. It's just whether you'd use a high temperature or a low temperature. If the reaction was exothermic, we'd use a low temperature. In terms of the pressure, it actually doesn't really matter because you've got 2 moles of gas on the left-hand side and 2 moles of gas on the right-hand side. So increasing or decreasing the pressure is not going to change the position of equilibrium. Yeah, so we're saying here, because there's 2 moles of gas on the left-hand side and 2 moles of gas on the right-hand side, they're the same. So increasing the pressure or decreasing the pressure will not make any impact on the position of equilibrium. If you were to add a catalyst to this reaction, a catalyst will not change the position of equilibrium. It'll just help it get to the equilibrium quicker. So it makes the rate of the forward reaction and the rate of the reverse reaction faster. So a catalyst doesn't change the position of equilibrium, just the rate at which it reaches equilibrium. So the question then also says, how will your conditions impact upon the rate of the reaction? So we've said it's endothermic, so we're going to use a high temperature. Well, if you use a high temperature, that will make the reaction go faster. Now, whilst increasing pressure would not change the position of equilibrium, if we do increase the pressure, it will make the reaction faster. Same with a catalyst. Okay, so the ideal conditions for this reaction would be a high temperature, probably a moderately high pressure just because of the speed of the reaction, but it's not going to impact upon the position of equilibrium. And we'd normally use a catalyst not to change the position of equilibrium, but to make the reaction go faster. Okay, so we've got another example here. You've got 2 lots of CO gas reacting with 1 lot of oxygen gas to produce 2 lots of CO2 gas. So you've got 3 moles of gas on the left-hand side, the reactants, and 2 moles of gas on the products. And you're told that delta H is minus 588 kilojoules per mole. That means the reaction is exothermic. So when we apply Le Chatelier's principle to this problem, if you increase the pressure, it'll favour the side with the least amount of pressure. So that will favour the side that only has 2 moles of gas. So to increase the yield of CO2, we increase the pressure. Yeah, so increasing the pressure will shift equilibrium to the products because there are only 2 moles of gas as opposed to 3 moles. And remember, Le Chatelier's principle basically says it's trying to minimize the change. So if you increase the pressure, it favors the side with the least amount of pressure. So the 2 moles. So that's a good thing if you want to make more carbon dioxide, but also increasing the pressure will make the reaction faster as well. However, there are safety implications of that. High pressure generally means more expensive equipment needed and greater risk of an accident. So you have to be aware of the safety implications. If we want to make more CO2 as well, the forward reaction is exothermic. And that means a low temperature is favoured, because if the reaction is exothermic, it means it gives out heat. So if you supply it with loads of heat, all it's going to do is waste it, it will dissipate it. So a low amount of energy is good for an exothermic, or a low temperature is good for an exothermic reaction. So a low temperature will favour the production of CO2. However, a low temperature means the reaction will be slow. So what they actually do in reality is that they'd use a compromise temperature, somewhere that's not too low, not too high. They'll do some studies to work out what's the optimum compromise between rate and yield. So they'd probably use a sort of a moderate temperature. Same way with increasing pressure. You don't just continuously increase the pressure. You have to find that compromise pressure, where the pressure is high enough to make a good yield, but not so high that it's unsafe. So in terms of, we've discussed the rates here, increasing pressure, that'll give a higher rate, but lower temperature will give a better yield, but it will be slow, so we use compromise on both. A catalyst will not change the position of the equilibrium, remember, but it will help it reach equilibrium quicker. So you would add a catalyst to this reaction. In terms of the Kp, which is the other thing the question wants you to do, remember Kp is products over reactants, so it's the pressure of the CO2. Don't use square brackets, by the way, with Kp, because that's concentration. So it's the pressure of the CO2 squared, because there's 2 moles, divided by the pressure of the CO squared times the pressure of the oxygen. Now the question doesn't ask for this, but it might be helpful to think about what the units of Kp would be, just in case the question asked on it. It's not too difficult actually. If we assume that the units of pressure are pascals, there are loads of other units you could use, but let's just say it's pascals. You've got 2 lots of pascals on the top, because it's pascals squared. You're dividing by 3 lots of pascals, so it's pascal, pascal, pascal. And therefore we can cancel the 2 on the top with 2 of the ones on the bottom. That leaves you with a pascal on the bottom, bring it to the top, and it becomes pascal to the -1. On the previous example, I think you had equal number of moles on the top and the bottom, which just means there'd be no units for Kp. Anyway, thank you for taking the time to watch this video. If it was helpful, please remember to like, subscribe, and keep checking back for more content. See you next time.